I'm very excited to share my work about how we can do the agent training, especially if we could ground the decision-making into the MDP formulation. Thank you. So before we come to the training part, let's firstly talk about what is a generalist agent. So when I talk about this, I actually asked Jiayuan, and she shared with me about a very nice, very clean definition that the agent is basically trying to do many tasks in many environments. So here we have two key facts. The first thing is about the many tasks. So it basically means you have a lot of different goals. So you want to do goal-driven decision making. Another thing is about environment. So it basically means like the agent need to understand what's in the environment, like objects, their states, and so on. So if we're trying to build the agent, we're basically trying to transform the large language model to the large agent model by adding these two abilities to interact with the environment and to do the goal-driven decision making. So let's firstly talk about one example. Like if the task is set up table, then we can see the agent is trying to put the turkey on top of the table. But the key here is that they directly put the turkey on top of the table, which is basically very ridiculous to us as human, because we basically feel like as human, we have this common sense knowledge. We will always use plates. So if we want the agent to use plates, then the agent will be able to put the turkey on top of the plate and then put the plate on top of the table. So this basically means like to understand all the goals, to understand the interaction with the environment, you really need to dive into the visual details about how these things are connected in the low level. This part, we also introduce a terminology called trajectory. Basically, we're trying to order the actions or order the state changes as a trajectory. Based on this, we try to think about like what is the embodied decision making. Here, our goal is trying to ground it to some fundamental formulation like MDP process. So for example, as the agent we just mentioned, the very important thing is the goal. So if we have the natural language goal, then the model is trying to input the goal to interpret it into the states in the environment, as we just mentioned. So this naturally introduces another part of the environment of the physical world. So now we have three parts. And then for the agent-wise, the input is like they trying to take in the current state, and then they try to predict what is the next action. So this action will interact with the physical world, and then we can get the state updated, and also the feedback can also contain some sort of the reward defined by the environment. So if we try to train the large language model, we basically have these different abilities. Let's dive into them one by one. So the first thing is about the state input. So the state will always need to be understood by the large language model, especially now we have a lot of like perception models trying to do the state estimation. So basically from the observation, you're trying to understand what are the objects and their states. One very surprising result to us is like the current large language models, they really perform bad on a lot of tasks, very simple, like just identify left or right. I think it's also related to what Franda is talking about. Like if we ask the model to predict where is the cup, even the cup is under the table or on the left or on the right, they will always predict the cup is on top of the table. So this basically means like the model is not really see the image. They are just using common sense knowledge to predict the spatial relationship. Another thing is about state changes. For example, as human, we can imagine the visual space. It's kind of like mental simulation. It's also related to what Franda is talking about. Like if we place a blue chair behind the red chair and put a yellow chair behind the blue chair and put a book on top of the chair in front of the blue chair. So as human, we actually gradually generate this thing step by step. But for the current large language model, they still struggle about this kind of task. And another thing is about visual perception detail understanding. So this paper from Sanin actually showed that even for the current large model, they still struggle about like where the dog is facing or how many windows are on the wall. So these very simple visual questions. And it's not only just in real image, like even in the mathematical world, like if we just have two lines and we ask the model to compare the lengths, sometimes it will still make errors. So all these things are very surprising to us. And we also see like not only this qualitative result is bad, but also this quantitative result show the model fall short of the geometric understanding. So we're trying to categorize like what is happening here. As this current large language model being trained by image caption pairs, so they naturally can can capture these objects, relationships, or actions, or trying to do some sort of the planning like cooking. But if we dive into the geometric-centric understanding, actually the performance is much worse. For example, if we understand the shape, the color, or the pose, orientation, then this kind of geometric feature understanding is already bad. And if we move towards to multiple objects, so we care about the spatial relationship between them, or we care about whether the agent can have the perspective, so it's like egocentric view, then the model will also fall short of that. And then if we're trying to move to more temporal dynamics, so if we have state changes, or if we have like mental simulation, as we shown in the previous example, or we try to understand the transition model, like given the action, what are the state changes, or the like complicated spatial reasoning, navigation, or episodic memory, the model basically also show a very low score on these tasks. So this show us like we not only need to understand this like semantic-centric information from the caption pairs, but we also need to understand the geometric-centric information. And we are thinking like, what is the fundamental reason? So for example, as human, when we're trying to learn about this physical world, we basically interact with them. So this knowledge is gained by interaction. But as the robots, as the large models, we don't actually have this multi-sensory interaction data because it's too costly. So what we're using is basically static internet data. So we try to use the video to mimic all the state changes. For example, if the book falling down, we basically record a video about how the state will change the location and the states. This basically means like when we train the model, we linearize everything. So for images, we just put them into a sequence of patches. And then for videos, we just concatenate all the patches all together to a sequence. And even for charts, like we do know nowadays, people really care about this mathematical reasoning problem because the score is not satisfying. And then we can see like this chart understanding is also based on patches. And also for these molecular structures, even it's like typically graphical model is better at this, but when we work on this, we still just break down them into patches. So we're trying to see like if this is really the good way to understand geometric-based perception. So we try to do some simple experiments, like we're trying to separate the perception task into the semantic-centric task and geometric-centric task. This actually grounded to some biomedical neurobiology publications about like for humans, we really have this two-stream thinking. Like we have one part to think about what and another part to think about where. So we're trying to separate the tasks into these geometric-centric questions, like trying to understand what are the lines crossing the black lines, and also the semantic-centric task, like we just identify whether there's a cat or not. And we actually identified two conclusions. The first thing is about for the geometric tasks, the vision language encoders, a lot of cases, actually, their loss will drop much slower compared to the vision-only encoders. So it basically means like from learning-wise, the vision language encoder, they always learn the semantic task much better. And then when we try to add the like large language model on top of the clip, so this is essentially the lava model, we find that the lava's performance sometimes is also worse than clip. So it basically means like this large language model layer sometimes will swallow the geometric features. As a result, it basically means like our geometric understanding is too biased towards to the language. So we're trying to actually try to move towards to this geometric understanding so that we can get a better understanding of the lower like visual details, and we basically trying to open up the model to see why. So the first thing is like we try to focus on the problem, very simple, just trying to identify whether the two objects has a spatial relationship like left and right. And we try to dive into the details that are wrong. So for example, if we open the model to check their attention mechanism for these wrong examples, the first thing we identified is the imbalance of the attention for the image tokens and text tokens. One thing we noticed is that like one image token actually around like 576 tokens. So it basically means like for each image caption pair, the image will take up around 90% of the token length. But for the attention wise, the attention weight they obtained is only less than like 10%. So it basically means like the attention is super imbalanced between the image token and text token, and the attention is totally biased towards to the language side. Another thing we identify is like for the first two layers, there's some like attention sink like mechanism as the large language model as well, and then the attention of the vision part will quickly drop. And also in the middle layer, the attention will has a bump. So when we do the intervention of the attention, we basically conduct the intervention in the middle layer. So if we identify this imbalanced pattern, one simple solution we are thinking is maybe we can directly enhance the visual part. So let's simply add the attention, more attention to the vision part. But to our surprise, this will not bring up the
送给你们，
performance. So we basically
你要就
identify
买呗。
about the imbalance problem. We cannot just directly like add the attention to the vision part. It's really about the distribution. So we try to still open the model and to visualize the attention, and then identify like a lot of attention basically for the spatial relationship. If they focus on the wrong reference object, then the performance is bad. So we try to intervene the attention, but we try to leverage model's self-knowledge. For example, we firstly ask the model to identify the spatial relationship, and then we can get the confidence about whether the model is familiar about the thing or not familiar about the thing. If the model is not familiar, then the attention is not trustworthy. So the distribution-wise, we want it to be smoother, so the model can have a broader window to focus on. And if the model is high confident, then the attention is more trustworthy. So we try to sharpen the attention. Then the model can focus on the parts that is already like important to answer the question. And to our surprise, this intervention, very simple intervention, actually can bring up the performance hugely. So for example, this is a data subset of the like example we just show, like there's two objects, one large object like a table and one small object like a cup. And we can see the performance can even bring up by 50%. After we talk about how we can do the state estimation, another thing we really care about this training is how we can learn this policy. So we could actually give the observation and give the goal, we can predict the action. So the first thing we are thinking is essentially this is basically the MDP formulation of a sequence of the state, action, and reward. So if we have this sequence, then the training is basically trying to see whether we could directly ask the language model to predict actions. So this is a very simple task if we just input all the state and ask the model to predict action. But then we're thinking like to this agent training, the most important thing is whether we could also force the model to do the reasoning, just like DeepSeek R1, what they are doing is trying to see whether the model can have this aha moment. So we are thinking maybe this kind of RL training can also force the language model to learn this MDP process by add this thinking process. So the first thing we care about is for the current RL training from like either the DeepSeek simple RL recipe or other kind of task, how they can achieve different reasoning tasks, like the single turn mathematical reasoning questions or this coding like agent questions. So there are two algorithms that are widely used. One is the SFT part, and this is the like S1 paper, what they are talking about, and also this single turn RL, this is what DeepSeek R10 is talking about. And then we're thinking like for the agent scenario, a lot of environment are actually not statistic. So they basically will produce the non-deterministic reward. Like there's like bandit machine, like when you interact with the environment, you only get a probability of like how much the reward will look like. So we try to introduce this single turn stochastic environment and also multi-turn non-stochastic environment like Sokoban and also the multi-turn stochastic environment. And to do the training, we try to see whether we could extend the DeepSeek R1, this like simple RL recipe to the trajectory-based training. So how we can do this is very like intuitive. For example, when we're trying to ask the large language model to predict the action, we firstly force the model to generate the thinking token, just very similar to the format like reward from the DeepSeek R1. And then from this thinking process, we can also predict the action that can be be executed in the environment. And then we can execute the action so we can get the reward. Then the sequence is basically augmented sequence that with the thinking process generated. And then during the training, we identify that for the agent training, as we mentioned, the environment actually will produce the different kinds of the reward, like the stochastic reward or multi-turn reward. So the reward normalization is really important in this sense. So we care about like whether the reward can be normalized across multiple trajectory and also across multiple steps. So we try to calculate the reward firstly for the entire trajectory, and then we're trying to aggregate them, but normalize them across all the potential alternative outcomes given the initial state. And then the performance basically shows that the model do appear this kind of new thinking process. For example, for the bandit machine, at first the model will always select the option that has lower risk. And then after several rounds of the training, the model actually started to learn that actually high risk option will always lead to high reward. So when it tried to make the decision to get high reward, it gradually turned to these high risk options. So this is the agent training framework about whether we could learn this MDP policy. And another thing is whether we could learn this reward model. So reward model is not just trying to predict the next state, but also trying to just directly assign a scalar score to evaluate whether the action is good for the current observation or not. So we also have a paper called the Rosetta, like trying to translate the human feedback to the code block functions so that this code block functions can be used as the reward function for the RL training. So this is how we can actually leverage the large language model's ability trying to handle this unconstrained language preference. So the model can also show very good performance on this like manipulation task in both the simulator and also the real world environment. Last, we'll talk about if we have all this MDP-based training, how we can evaluate them. So we introduced this embodied agent interface trying to bridge the large language model and also the embodied decision making. The evaluation part, we really care about standardization because nowadays, like there are so many paper work on different parts and they all claim they are the best. So we really try to find a way to see like for these large foundation models, what actually is actually useful for different functions. So we try to build this embodied agent interface so that it can connect the any type of the large language model to any type of the embodied simulators like virtual home behavior and so on. And our code is like made into a single line of the code to run the entire pipeline. So you basically can get the interface that's driven by this MDP process freely. So firstly, from this MDP process, as we mentioned, for the agent part, we really care about these three things: the input of the state, the input of the goal, and the output of the action. So for the input part, the input when they are the natural language goal, we try to translate them into the symbolic goal grounded into the environment. So that's basically goal interpretation. And for the output wise, we have the sequence of the actions, or we can have the sequence of the state. So if it's a sequence of the actions, then it's action sequencing. If it's a sequence of the state, then it's the subgoal decomposition. And we also care about the single step transition. So this is basically the transition modeling. That's essentially what a lot of people are talking about, like word modeling. Then for the interface wise, we try to incorporate all the fundamental abilities that we discovered based on this MDP formulation. And then we can actually ask the model to do like goal interpretation, like given the environment, the model is trying to identify like there's the bow tie on top of the table, and then they try to identify the goal will be changed to the bow tie is not on top of the table. And if they identify there's a basket, they will put the bow tie into the basket. And then we also care about like subgoal decomposition. So we're basically trying to not only have a sequence of the action predicted, but also trying to break down the goal. So if we try to bottling the fruit, we will try to cut the fruit and also put them into the bottles. So this actually break down into 3 steps. The first one is about cut 2 kinds of fruit and then bottle each of them. And for the subgoal decomposition, a lot of people are talking about it's very hard to identify whether this goal is achievable or not. So we actually need to use some BFS planner trying to search for the actions that can achieve the subgoal. So for example, if we have 2 options, if we try to grab the knife first, it's not executable. If we not grab the knife first, but directly cut the fruits, then it's actually executable. And then for the action sequencing part, I think it's the most widely used component that you just given the goal, trying to predict a sequence of the actions that can achieve the goal. But what we care about is that when the model has the wrong prediction, like they basically cannot cook the strawberry here, then what they should do. So we trigger this replanning process, and we support the non-deterministic action to ask the model to replan given the current status or given the previous errors. So the model can actually fix the error, like they should firstly put the pan into the oven and then cook the strawberry. And for the transition model part, I think this is the most exciting part for me, that for the large language model, if they change to the large agent model, what they essentially learn is about the common sense for this entire world. For example, if you want to clean the bowl, the common sense knowledge is that you have the precondition, like the bowl is stand and you have the rag that is soaked and the rag is close to the bowl. And if you have all this precondition being satisfied, then you could actually clean the bowl. So the post effect is the bowl has been cleaned. So this is essentially the common sense knowledge of the world. And then if you have all this common sense knowledge, then the planning will be naturally come into a searching process. And then you can actually identify the previous actions post effect should be the next actions precondition. So we also try to identify the errors from all these simulators, so we could help the large language model to learn feedback from this environment. Like if it's a goal error, we actually identify whether it's a false positive, like some objects that is not appearing in the environment, or it's some missing goals. So one thing we actually identify very interesting is like the hallucination is actually not a very important error for this embodied simulators. For example, the hallucination is only less than 1%. And previously, we actually imagined there might be like tens of the errors about hallucination. And another thing very interesting, I think very useful to the feedback-based training is like we can also identify for the trajectory error, whether it's a missing step, whether it's a affordance error, whether it's a wrong order or it's the like affordance error. So we could give very fine-grained feedback for the large language model so they can better train the planning ability. And another thing we identify is like for the vision language foundation model side, if we try to input both the vision part and the text part, the performance will actually drop compared to only input the text part. So for the current models, it basically shows that the vision part is only the noise rather than the helper. So if we really want to improve this vision language model part, it's very important to improve the perception or state estimation ability that we just mentioned earlier. So all the things are like encoded into a single line of code and welcome to play with our model. So we're also trying to move forward to better train this embodied agent, to train this large agent model to enhance this environment ability and enhance this goal-driven decision-making ability. As we mentioned, from the environment-wise, we really care about this geometric-centric ability, and also we're trying to make the decision-making to be more longer horizon and to enforce the model to do reasoning to see whether they can have this aha moment during the training. And another thing we try to care about is like we really want to understand the spatial reasoning in the long horizon like videos, like the egocentric videos we care about, like given the scene, whether you can see where is the key and or whether the freezer is closer to the sink or closer to the microwave. And we also have this long video haystack trying to do the temporal searching so that we could gradually zoom in the important part to identify like what is the thing we should care about. And finally, I also want to advertise like we have the NACO tutorial about foundation models meeting embodied agent. And we also did this tutorial at AAAI. So all the slides are on the website and we are uploading the video within this week after AAAI provides the videos.